Hi everyone, my name is Daekun Kim, and I'll be talking about our exploration on different approaches to mouse technique design for spatial augmented reality. Spatial augmented reality, or SAR, enables augmented reality experiences with projectors and existing surface geometry in the world. This is interesting because SAR doesn't require any headsets or AR glasses, unlike the type of AR we're most used to. Desktop computing is still one of the most popular ways to conduct productivity tasks, so extending it to the surrounding environment would combine its productivity potentials with benefits of AR, like increased screen space or more 3D native interactions for tasks like computer-aided designs. But typical AR interaction techniques, like direct touch or mid-air ray casting, are not ideal candidates for this, with reasons like low precision or sensitivity to occlusion. Mouse, however, has little to no impact from these problems. On top of that, since desktop computing already uses a mouse as the main interaction method, this seems to be the most fluid and familiar way to integrate traditional computing to SAR. So, we explored how to design a mouse technique for SAR with a focus on two approaches, perspective-based and geometry-based. We introduced Everywhere Cursor, a geometry-based mouse technique for SAR, as a concrete example to compare with perspective-based techniques. I mentioned ray casting as a popular method of interaction for mixed reality systems. Another interaction technique using the mouse is perspective cursor by Nascenta et al., which was designed for multi-display environments. Techniques like these place the cursor at the end of a ray from some origin and controls the ray's angle to move the cursor around. In this figure, the mouse is moving to the left, and the cursor trajectory is shown with the solid red line on the wall. We call this the perspective-based approach to mouse technique design. We can also think of the cursor as moving along the curvature of the environment geometry using the relative x and y mouse movements mapped to the cursor's local x and y axes. This is how we currently use a mouse on desktops and laptops, with the surface being a flat, planar display. We call this the geometry-based approach. Now, on a flat user-facing monitor, the two has mostly the same behavior. But note that with perspective-based approach, the cursor also appears on the surface closest to the user. That means it may skip some occluded surface details. With geometry-based, the cursor can travel into occluded surfaces, which can be helpful for producing a continuous trajectory even on detailed geometry. While there are existing techniques for the perspective-based approach, there isn't any for geometry-based. So, we introduce Everywhere Cursor to concretely compare perspective and geometry-based techniques. The cursor is visualized using an orthogonal virtual projector. A set of short raycasts, called legs, orient and position the cursor, allowing the cursor to move around the environment like a bug. Using the legs, the cursor stays parallel with the nearby surfaces. The cursor points upward on a vertical surface and forward from the perspective of the mouse on a horizontal surface, like on a desktop monitor. To detect the next cursor position, a circular raycast is performed with the radius equal to the movement distance. Because of the variable size of the circular raycast, the cursor can skip obstructed regions like gaps with a fast mouse movement to allow for faster interaction. We treat the monitor as a special case, where the cursor jumps to the display when it enters a hidden region behind. The resulting behavior extends the interaction domain from planes to arbitrary surfaces. In case the cursor is lost, raycast clutching allows the user to reset the position of the cursor by tilting the mouse sideways. We compared the speed and accuracy of Everywhere Cursor's geometry-based movement with perspective-based techniques. For the latter, we had SAR adaptation of perspective cursor and standard raycasting. For the experiment, we had Vicon motion-tracked mouse, as well as a hat for head tracking. We've set up a realistic office space with a variety of surface types, a lamp sculpture as curved surface, a monitor as flat surface, a bookshelf as irregular surface, and the front face of the printer as far oblique surface. We tested 3 types of tasks: 30 centimeters short distance selection, 1.5 meter long distance selection with simple and complex variations of the surface complexity between targets, and tracing tasks with linear and circular variations. We had 12 participants who performed short distance selections in the first stage and the rest of the tasks in the second stage. Our analysis of selection tasks focuses on selection time and error. Here are our high-level results. The labels on the x-axis represent the type of surface the task was performed on. Everywhere cursor and perspective cursor performed equally as fast, as you can see, on the flat or normal, oblique, irregular, and curved surfaces. Raycasting was quite a bit slower than the other two, with it taking nearly 1.5 times longer. Everywhere cursor and perspective cursor were also similar in error rate, except on an irregular surface, where perspective cursor was significantly more error-prone. Raycasting was more error-prone than the other two, with around 10 percentage point increase in error rate. Next, we have the results for long-distance movement. Here, everywhere cursor and perspective cursor were equally fast when the surface geometry between the targets were simple with little obstacles. But with the complex condition, everywhere cursor was significantly slower, taking almost twice as much time as the other techniques. However, everywhere cursor was overall significantly more accurate than the other two. For tracing tasks, we had two measures of performance on top of time. Tracing error is a measure of accuracy, showing how close the cursor trajectory was to the ideal path. Path deviation is a measure of precision, showing how jittery the trajectory was. So, with linear tracing, all techniques were, generally speaking, equally fast. Now, for tracing error, everywhere cursor was much more accurate than the other two, especially on surfaces with detailed geometry like irregular or curved. It had half to almost a third of the error compared to the other techniques. The trend for path deviation was similar to tracing error, with everywhere cursor being more precise than the other two. For circular tracing, all techniques were, generally speaking, equally fast. In terms of tracing error, everywhere cursor was more accurate again, but this time the difference was not as drastic. The trend with path deviation is, again, similar to tracing error, with everywhere cursor being more precise. But here, the difference in precision is more drastic, where the other two techniques had double to triple the amount of path deviation. Here are a couple of demos of how we envision SAR desktop environment with mouse interaction to look like. Here we have a variety of content spread throughout the room, like an online video on a whiteboard, a movie on the wall, brainstorming dock on the desk, and an ambient decor on the bookshelf. The user can print a document through a drag and drop to the printer. We wanted to push the physical metaphors of desktop interactions by actually incorporating real-world objects like the printer. Given that the mouse cursor has to travel a far distance, a perspective-based technique would work better for this. This projection mapping decor on the bookshelf can also be reconfigured using the mouse. Given the detailed nature of the surface geometry, we can see that a geometry-based technique would be more suitable. To conclude, we explored the perspective and geometry-based approaches to mouse technique design for SAR. We found perspective-based approach is better for long-distance movements, while geometry-based approach is better for tasks where a continuous trajectory is required. We hope that future work will look into how the benefits of these two can be combined into one technique. Thank you very much.